In this video, I'm going to discuss how to use the UART on the PIC32 MX170 chip. So we've got a breadboard version of the DIP PIC all built up and tested, and we've got some code that when we push a button, it blinks at the frequency we think it's going to blink. So we've got the basic PIC setup. And what we're going to do is use this USB to UART adapter from Adafruit. The chip on it is the CP2104 to be able to communicate with our computer. So this particular PIC, the 100 series of the PIC32MX, does not have the ability to talk USB. So the way we can get it to talk to our computer is using UART, and then this chip will convert the UART to a virtual serial port that we can open up in Screen or Putty on our computer. So let's start by talking about what is a UART signal. And then we'll look at how to wire up the chip to the PIC, and then we'll look at code. So UART stands for Universal Asynchronous Receive and Transmit. This is a digital communication protocol. And in this class, ME433 Advanced Mechatronics at Northwestern, we're going to talk about a bunch of different types of digital communication. Some are very fast, and some enable you to talk to many different kinds of chips, and then some are kind of simple. So UART is probably the simplest version of digital communication. The downside is that it's relatively slow. So when you're trying to push data from one device to another, compared to the other styles of communication we'll talk about later, this one's kind of slow. It has a few pins. That's kind of a good thing. But that also contributes to why it's so slow. So let's draw a picture of what this looks like. We have two devices, device 1 and device 2. And they want to talk to each other. So in this version of communication, they will have to have common ground. So they'll both be attached to the same ground. That way the voltage signals that they pass back and forth are relative to each other. They don't necessarily have to have the same power source, though. So one could be powered by the wall, and the other could be powered by battery, but they do need that common ground. And to send data, we will have a pin from one device called TX, or transmit, and it will connect to the RX, or receive pin, on the other device. Then device 2, if it wanted to talk back, it would have a transmit pin that sends to the receive pin of the other device. There's nothing tricky that happens here. So the TX pin is an output and the RX pin is an input. They don't switch back and forth as we'll see in other communication protocols. Sometimes pins are inputs and outputs. In this case, they're either input or they're output. And if we want device 1 to talk to device 2 but not need to talk back, we can get rid of that other pin, and then we can have just one-way communication. What might look a little strange here is that when TX is talking to RX, how does device 2 know when to read that RX pin? So TX is going to send out some digital 1s and 0s. How does the RX know when to read? The way other digital communication protocols will solve this is by having another line called a clock line, and when the clock changes, that's when the two devices decide to read the digital data. So that doesn't happen here. We get to save a pin by not doing that, but we will have to decide beforehand what the baud rate is, and it will have to be the same. The baud is the bits per second data rate. So that means how long is a high or a low of a digital 1 or a 0. And the device 2, when it sees the first edge, will know to start reading, and it will know how long to read for before it reads another bit, because they will both decide on the baud beforehand. So the bauds have to match. If they don't match, device 2 will read at the wrong time versus what device 1 is sending, and the data will come out as gibberish. You'll still read it, but you won't know that it's incorrect. Some other things that happen here with UART. Occasionally we'll see some more pins. CTS and RTS, ES and CTS. So let's say that device 1 is sending lots of data to device 2. Device 2 has to read that data and then store it into memory. If it, for some reason, has to do other tasks, it might want to tell device 1, hey, stop sending me data because I need to do some other stuff. I'm not ready for your data. And if you keep sending me data, I might lose that data. So the CTS and RTS, clear to send and ready to transmit, are lines that talk to each other, and that's called, these two specifically, hardware handshaking, where the devices can indicate to each other, hey, I'm not ready, so please don't send any more data. And in that way, we can kind of guarantee that we never lose any data. We'll probably leave that off in this example. But if you want to use 2 more wires, you can connect those and get kind of guaranteed transmission. Okay, so what we're going to do is we're going to make device 1 the PIC, and device 2 is going to be the CP2104, which is a breakout board from Adafruit, and for some reason they call it the Friend. I don't know where they come up with the name. But the CP0 is a UART to USB chip. So the USB cable is capable of sending data way faster than the UART is able to send, but USB has a lot of complexities to it. So this device is basically a microcontroller that talks UART, saves the data locally, and then when it can, send the data over to USB. And then the computer is able to open this up in Screen if you're in Linux or Mac, or Putty if you're on Windows, or a whole host of other programs, including MATLAB and Python, and basically any programming language can open up a USB serial port and grab the data. So why don't we take a look at the PIC for a moment. And I'm going to talk about a few things here so that we can do some bookkeeping. One is that this PIC has 28 pins, but not all of them are I/O pins. So for example, some of the pins are for power and ground and things like that. So we have very limited numbers of pins here, and the end project in this course is going to involve using all of the pins. And actually, it's going to use more than all of the pins. So we need to get some pins back. And one thing we did here is we have the PIC running off an 8 megahertz external crystal resonator, this little blue chip. I'm going to yank that, and we're going to get 2 more pins back available to do other things. And instead, we're still going to get the PIC to run at the same speed that we're running at. So we're running at 48 megahertz using the PLL. We're going to use the internal oscillator of the PIC that also runs at 8 megahertz and PLL to 48 megahertz without the external crystal resonator. This internal resonator isn't as good in terms of like when the chip heats up, the frequency might shift a little, but it won't be so bad that we'll even notice that. If we were trying to do USB communication directly with a PIC, they don't recommend using the internal oscillator. That's why I typically use the external oscillator. We're gonna ditch that right now, and I'm gonna show you how to adapt to the code that you wrote for the earlier homework, so that everything still works. So right now there's no clock, so it won't run. Let's switch over that code so that it runs with the internal oscillator, and then let's add in the USB to UART chip. So notice the connections that need to be made. We have a ground connection because we need common ground. And then we have 2 pins, TX and RX, from the friend board need to be connected to 2 pins on the PIC. So we need to figure out what pins do we connect to on the PIC and how do we turn those on in the UART peripheral and assign the pins and that kind of stuff. So we're going to make a new project. We're going to first get it to blink like we had it before, but using the internal resonator. And then we're going to add the UART code and send data back and forth. So I will switch to a screen share, and I don't have any of this prepared. I'm just going to show you how I like to design it from scratch. So let's take a look at the datasheet first. This is the picture of the PIC that we're using. We're using the PIC32 MX170F256B, and it comes in these different packages. We're using the DIP package. And the tricky thing about this particular image and these tables that tell you what the pins are is that it goes from pins 1 to 14, and then for some reason this column starts at 15 and 28. But remember, pin 15 is down here and pin 28 is up here, so this column should really be flipped. Now, when we're using a peripheral, what you would normally do is you'd go and look at all the pin functionalities and say, okay, let me look for the UART RX and TX pins. So it should be like U1 RX and U1 TX and U2 RX and U2 TX and so on. But when we look at these functions, we don't see that because this version of the PIC allows us to use reassignable pins when we're coding. So that means that some functionalities are fixed, like this SCL2 and SDA2. These are I2C pins. That's another kind of digital communication. They're not reprogrammable, so they're kind of stuck on those pins. But we don't see UART pins because they're reassignable. So whenever you see an RP name in any of these pins, that's a reprogrammable pin. So that pin might be capable of being a UART pin. And when you look around, basically all of the pins are RP something. So RPB11. Let's go find the tables that say what RPB11 is. And that's related to the pin IO. So I'm going to go to the IO ports chapter of the datasheet. And I'm just going to scroll down. This first bit describes port and lat and tris, how to make the pins turn on and off. And then it starts talking about this peripheral pin select ability. And that's how we can assign something. For example, some of the pins will be capable of being U1 RX. So the first table we see is for input pins. So any peripheral that uses pins as input will show up in this table. And then further down, we've got another table for output pins. So here we've got, let's say we wanted to use the int4 peripheral. So the int peripheral is for generating an interrupt within the PIC based on a pin that changes from high to low or low to high. And the special function register is called int4r. And if we made the value int4r equal to 0000 in binary, then we would essentially say pin A0 is now connected to int4. And then we wouldn't be able to assign int4 to any of these other pins. And we can't take T2CK and assign it to A0 because only one thing can be connected to one. So what we need to do is we need to find U1RX and figure out what pin we're going to assign it to. And then we'll find U1TX on the output table and figure out how to assign a pin to that. So looking through this table, we're looking for U1RX. Here's U2RX, and here's U1RX. So U1RX is in this block. So U1RX could be assigned to pin A2 or B6 or A4 or B13 or B2. And then some of these chips have pins in C if we had a chip that had more pins, but we don't. So we don't have any of these pins. So we essentially have 1, 2, 3, 4, 5 different pins that we can assign our U1RX to. It would be great if we could have used any pin, but for some reason they limited us to these certain selections. Okay, so I'm not going to say which pin I used yet, but we're going to have to figure that out in a second. But at least we know the possible pins. So now let's go down and look for U1TX. And the outputs, instead they say here are the pins and then here are the functions. So I'm going to look for U1TX is here. And it can be A0, B3, B4, B15, B7, but we don't have C7, C0, C5. So any of these guys up here. So if we said RP B3R bits dot RPB3R equals 0B0001, that's how we would assign U1TX to pin B3. So let's take a quick consideration of where we're going in this class, because we're going to want to use this USB to UART converter a bunch of times, but we're going to need some of these pins for different kinds of projects. So let's try to pick the pins based on the other functions that we're going to need. So I drew up a massive table. And I see here are the U1 RX capable pins and U1 TX capable pins, and then U2 RX and TX. And here's our output compare for PWM pins. And here's our SPI pins, another kind of digital communication, and I2C pins, and then external interrupt pins. And I started to write down the pins that we need to be able to run some of our other projects, including a camera that needs 13 pins. And there's only 19 pins on the PIC that can talk at all. So we have to be very careful in the assignment of our pins. So I kind of went through and pre-assigned some of our pins for the future assignments. And that left me with the available pins B6 and B7 for the UART. So we're going to use B6 for U1RX and B7 for U1TX. And you don't have to do this. You can do whatever you want. But it's just something to keep in mind that in the future we're going to have lots of other projects, and you might have to flip the pins around. And hopefully I did this right, so we don't have to flip them around, and we can just leave this built on our circuit board forever now. So we would go back to the PDF. Oh, yep, we're there. And we would go back to the picture of the PIC. And we'd find pins B6 and B7. Here's our PIC. B6. The 200 series, of course. Okay, there, the 100 series. B6 is pin 15, so the bottom right pin, and B7 is one above it. So I'm going to find the TX pin on the USB friend and connect it to the RX pin on the PIC, which is B6, pin 15, and we'll do the opposite for the other pin. Take a look at that. Okay, and they kind of show arrows. The TX pin has a little arrow pointing out, so the this is the friend's TX pin is going to the PIC's RX, and then the PIC's TX is going to the friend's RX. So those are the only connections we need: the ground, the TX, and the RX. Okay, and I yanked the clock out of my PIC. So the first thing we should do is make a new project and figure out how to get the PIC to blink its LED, but using the internal resonator instead of the external clock. And then let's figure out how to add code so that we can talk with the UART. And this is part that didn't work in my last screen capture, so hopefully it works now. We're going to do a new project in the MPLAB X IDE. And the first option is we want to select a standalone project. So we're not importing an old project from a previous version of the IDE. If you have installed Harmony, Harmony will be in here. We're not using a Harmony template. We're just doing a standalone project. Say next. And now we have to choose the PIC that we're using. So we're using the PIC32 and X170F256B. And the tool that I'm using to program is the Snap Programmer. And if your Snap's not plugged in right now, you can select no tool, and then later on you can select the Snap. Okay, then I choose the compiler version. And then I need to give my project a name. I'm going to call it UART. And I'm specifically putting it in a folder. For you probably want to make sure that you're putting this inside of your Git repo. I'm not saving this to Git right now, so I'm just putting it in the default location. And then I'll say finish. And the IDE is now making a folder called UART in the folder that I selected. And it's basically a blank template with nothing in it. So if, what do they put in? I think they put a makefile in. Makefile is more complicated than previous makefiles we've seen. So you don't have to ever worry about this. The IDE is calling the makefile. Doesn't even give us any C or H files. So the first thing we want to go is into source files and right click and say new C file. And I like to call the first one main. And it puts in lots of comments and junk in here. So I immediately get all of that and delete it. And I'm going to go into the main from my previous homework. And I'm going to grab everything and copy it and paste it into my new main. And so basically I'm treating that first homework like a template, and I'll just constantly edit it. So the first thing we want to do is get it to blink again. So here's where we tell the PIC using the dev config registers, using these pound pragma commands, that we're using an external crystal resonator that's 8 megahertz, and then we're going to divide it by 2 and multiply by 24 and divide by 2 to get 48 megahertz. So what I would like to do now is switch it so that we're going to use the internal resonator instead of the primary one. So we're basically going to switch this to say FRC instead of pry. And I should probably change the comment, use internal. So essentially we're getting 2 of the pins back for general purpose use. And then we want to set this POSC mod to be off instead of high speed because we're using the internal. I think it's actually RC, not a crystal, but whatever. Okay, so now I will compile this code using the hammer and just make sure it builds. And this code previously worked. When I push the button, it makes my LED blink. Okay, so the hammer builds the code. The hammer and broom is clean and build. So if you ever add more C files or H files or something and you want to be sure that you're starting from scratch, you can do clean and build. And once it's built and there's no compiling errors, now I can click this downwards green arrow. That's the download button. So I'm going to take my snap and I'm going to plug it back into my PIC. And I'm going to hit that downwards green arrow. It says it's already been compiled, so now it's just going to connect to the programmer and download the hex file. I've had people ask also, what's the green triangle button? The green triangle button is essentially the same thing. We turned off the debug capability here. So if you use the green arrow and debug was on, kind of some different things could happen. We could use the debugging capability of the PIC and the snap, but we're not doing that in this class. So really, there's no difference between the green triangle and downwards green arrow. I like to use the greenwards down arrow for some reason. Okay, so it says the program was installed and it verified that it's there. And now I can switch back, show you. We've got the snap still plugged in. The PIC is running. If I push my button, I get half second on, half second off, 2 blinks. So the PIC is still running at the correct speed, but now I'm not using an external crystal. So this chip might kind of fluctuate in speed by, I don't know, less than 1% as the temperature changes. We're not going to worry about it too much. We could worry about it because I'm going to have to now tell the PIC what baud rate to send data to this device, and this device will have its own baud rate setup. So if they don't match, the data doesn't match. So if I tell this one 9600 and 9600, but because the temperature makes this one really 96.1 or something, you know, that's where we could have errors, but I don't think we're going to see any of that. Okay, so we now have a project that programs the PIC with all of the correct pragmas. Let's talk about how to get the UART to work. So the first thing we'll need to do is tell pins B6 and B7 that they are the UART pins. We don't have to use tris or lat or port in this case. That's how you just do regular digital I/O communication. In this case, we're using the reprogrammable special function registers. So let's go back to that chapter, I/O pins. And let's figure out first, how do we assign UART1 RX to pin B6? So here's U1 RX, and just to verify B6. So if we make U1 RX R bits dot U1 RXR equal to 0B0001, that's how we would set up the pin. So let's do that. And the nice thing about using the IDE is it should help us. So U1 RX tab, not tab, control space, and it will say, let me find an autocomplete of all the things that I have in all of my CNH files attached to this project that start with U1 RX. So I'm looking for U1 RXR bits dot U1 RXR equals, but it can't tell me what the possible values are, so that's why I had to look at the datasheet, 0B0001. So U1 RXR bits dot U1 RXR equals 0B0001 should set U1 RX to B6. Okay, so we've assigned that pin. Now we're going to do TX. And in this case, we're using B7. So we're saying RP B7R bits dot RP B7R equals 0B0001. Okay, so let's go back to our code. We'll say RPB 7R control space bits dot that is equal to 0B 01. And I leave comments here that says U1 RX is B6, U1 TX is B7. Okay, so now I've got my UART pins assigned. I need to call the special function registers that will enable me to be allowed to use the UART. I could look up how to do this from scratch, but we did this in 333, and we used functions that we wrote in nu32.c and h. So let me go to nu32.c and see if we can't just copy those functions and put them into this new project. So inside of nu32 startup, which was a function that we called at the beginning of all of our code, we have turning UART3 on without an interrupt. I'm going to copy that, and I'm going to paste that into my code. And really, I can make this a function later after I test it and make sure it works. Notice that when I paste this in, all of the U3s are underlined in red because this particular PIC now does not have a U3. It only has a U1 and U2. So it's basically saying, hey, I have detected that you're trying to use a variable that doesn't exist. I'm going to change all the U1s to U3s to U1s. Okay. Now we have to set a desired baud rate. And so the system frequency for our clock here is 48 million. And we're going to choose a baud rate. I'm going to choose 115200. And in a second, we'll talk about that. But this equation comes from the datasheet. Now we're going to talk about this in a second too. How do the data bits get sent out? This is usually like 99% of the time how data bits get sent out in UART with 8N1. We're saying we're using the TX and RX. If we only wanted to use just the TX or just the RX, we could save a pin here. And then on the NU32, we use the flow control pins. We're not going to use the flow control pins. They're off by default, so I'm just going to remove that. And then we turn on the UART. So now the UART is on. And we'll go back to the sample code. And let's steal the read and write functions. Those. And their functions, I'll put them below main. But for the code to compile, I need to keep the function prototypes. So I'll go grab their function prototypes. And I'll put them above main after my pound pragmas. And let's take this and now we're doing UART1 instead of UART3, and we're not on the NU32, so I'll just remove that name. So my functions will be read UART1 and write UART1. And I'll go to the bottom, and so we're reading from UART1, my name match, read UART1, and 1, write UART1, and then anywhere we see a U3 is now a U1. And same thing in the read function. Okay, so let's talk about how do you read and write from the UART. So writing to the UART, we're going to take a pointer to a character array, so letters that we've generated using sprintf. The array is going to end in the null character, which is the 0 is the value 0, but it's not the letter 0. So while we loop through every element in our character array, as long as it is not the null character, we're going to put it into the U2TX register. As soon as we put it into that register, the PIC is going to then blink it out using 1s and 0s, to the other device. As soon as we put the value into that register, we can move on. We don't have to babysit it. So then we'll loop to the next element, but we're going to wait until the previous one was sent out, because the PIC is so fast that putting the value into this register and then waiting for it to be sent, it hasn't been sent out yet. It's being sent out much, much slower than it's capable of running the code. So we're going to wait until the previous thing, until the buffer is empty. Once the buffer is empty, that means we can put something else into the buffer. And then once we hit the 0, we'll stop trying to send. Okay, let's look at the read function. So the read function, we're going to take the pointer to a character array and the maximum number of things we could possibly put in that array. And we're going to wait until we see a /r or /n character from the thing that we're talking to. So initially we're not complete because we haven't seen /r or /n. We're going to see, is anything available? If it is, we're going to read it. If it's a /r or /n, we'll be done. If not, we're going to put it into our array, and we're going to make sure we don't overwrite the length of our buffer. Once we're done, we'll stick in a /0, a null character, so that scanf can work on that character array. So these are functions we used a lot in our previous class. We know they should work. The main, oh, that's a U2. We're using U1. Be very good to use all U1s here. Okay, so the last thing to do would be maybe every time I push the button, after I blink twice, I would like to print something to the computer. So I will, first I'll make a character array to save my data into. I'll say character array called M with 100 possible values, and I'll use sprintf into my character array, the word hello, classic hello world, and then I will use my function write UART1. So starts with WR, control space, finds my function write UART1. Notice that there is already a write UART function. That's something that Microchip wrote, and I should investigate where they put that, but let's not trust that it works at all. We're using our function write UART1. We're writing our character array M. Notice that sprintf here is highlighted. It doesn't know what that is because we need to now pound include stdio. That's the library that contains sprintf and scanf and all those kinds of things. Okay, so I'm going to build and download that onto my PIC. I've got some warnings. Let's go check those out. Type void for my write. Oh, because I didn't the right name. That, oh man, that doesn't have the right name either. All kinds of bugs. Okay, we'll try again. Amazed that that compiled without an actual error. Okay, that time we didn't get any warnings or errors. And the code has downloaded. Now what I need to do is I need to be able to open that port in Putty. So let's do this in Putty. In the previous class, we used make Putty to be able to operate Putty. That opened Putty automatically for us with the right settings. Here's how we do it manually. So when you open Putty, it wants to talk SSH. So it wants to talk over the internet. We're going to change it to talk serial. And we have to tell it what's the name of the COM port and what speed. So we already told it 115/200 is our baud. We have to figure out the name of the COM port. And I can do that by going to my device manager. And the device manager under ports is going to list the Silicon Labs CP2104 COM 221 on my computer. That's a very big number. Yours is probably going to be like COM 5. Okay, so I say COM 221, and I'm going to save this as COM 221 so I can find it faster next time. say open. Now I've got my Putty terminal window, and if I push the button on my PIC, I see my light blink twice, and then it printed hello. And if I push the button again, I get 2 blinks, and hello. And if I type, every time I push a letter on my keyboard, that's being sent to the PIC. I didn't do anything on the PIC though to read those, so we could deal with that later. Oh, another interesting that happens on the friend. Off. Oh well. Well, the friend has LEDs on the TX and RX lines, so they blink when you send and receive data. So that's kind of fun. Notice that when I printed, the cursor stayed where it was, so I should probably always have a /r/n. And notice that I don't have to close Putty while I'm downloading. In the previous class in ME333, the port was used for programming and debugging. So now we've got the snap during the programming, so I don't have to close my debug window. I'll push the PIC button, hello, and then a new line. Push again, hello, a new line. So I can just leave this Putty open until I'm done. Okay, now if you're on Mac or Linux, you need to figure out what is the name of the COM port. So you do that in a terminal window. You would type ls/dev/tty.star to figure out what the name is. ls is the list program, and your port name is going to start with /dev/tty dot, I think. And then it's going to list anything that starts with that. So the star says, show me anything that starts with this stuff. And it'll probably say USB serial and then some number. And then to grab your data, you'll run the program screen, and you'll have to say the name of the port. So it'd be /dev/tty dot USB serial 1234. It's going to have some number like that. And then you have to say the baud rate. So you'd say 115200, and then you'd hit enter, and then you'd get to see the data that gets passed and forth. Okay, let me see if I can get my camera to behave, and I'll draw you a picture of the voltages you would see from RX to TX, and that'll be the end of the video. Off, on, blurry. View. Manual focus camera. Okay, just as an example, every time I push the button on the PIC, it blinks twice, and then it sends something to the computer, and the LED would blink if it was sent. I closed Putty, so we don't get to see it blink. So let me open Putty again. Okay, so every time I push the button, blink, blink, and then we see the TX LED briefly blinked, because every time the PIC sends data to the computer, that LED will blink. And now if I go into Putty and I type something, every letter that I send from the computer to the PIC will be received here, and then we get a blink to show that, oh, there's data coming in from the computer. So we've got the PIC talking to the USB to UART converter using the TX and RX pins. What would that look like if we scoped it? So here's a TX to RX line. So this is the voltage versus time. Digital ones are going to be 3.3 volts and digital zeros are 0 volts. That line is idling high, so when nothing's happening, it's a high voltage. And when we send some data, the line goes low for 1 baud period. That's called the start bit. So that's how the listening device knows that something's about to be sent, that this high to low transition for 1 baud rate says, okay, start listening to me. Now for 8 baud cycles, the byte that you're sending, so the letter in ASCII that you're printing, gets sent. So 8 more baud cycles, you get 8 ones and zeros. Then when we're done, we get a stop. We get a parity bit, and then we get a stop bit. So that's a baud cycle, that's a baud cycle, and then we idle high from then on. So the parity bit is something that if the wires that are connecting the RX and the TX are really long, we could get noise on them. And that noise might be misinterpreted as 1s and 0s. So one way to do error checking here is that you sum up the 1s and 0s in the byte that you just sent, and whether it's even or odd gets a parity bit, and so you get a 50-50 chance of your parity bit not being corrupted. You can try to figure out if that parity bit doesn't match what the parity computation is, you should throw away this byte. So we usually don't worry about this. So we turned off the parity bit when we initialized the UART. So what does it mean to send 1 byte of data from TX to RX? It takes 8 baud cycles plus a start plus a stop. So it takes 10 baud cycles to send 1 byte of information. So when we are at a baud of 115,200, that's bits per second. That's what the baud means. That means we're sending this many 11,520 bytes per second. So if you start thinking about, well, I have an array of 1,000 values, and I'm trying to print those 1,000 values to the computer. I can send 11,000 letters per second. So how many letters is one of my piece of information? You can figure out how long does a transaction take. This is pretty slow. If you needed to send 100,000 pieces of data, it'll probably take 10 seconds of just printing all the data. So in the future, we're going to see faster ways of digital communication, not with necessarily our computer, because we're kind of stuck with the USB to UART converter to get stuff to the computer. But to get data from one chip to another chip, we'll be able to push this baud rate a lot faster by consequence of using more pins. Okay, so that is using the UART on the PIC32, talking to our computer using a USB to UART converter.